Turychev, who made his way from Los Angeles to Geneva last night. So Slava, he got his PhD from Moscow State University back in the 90s. He was at Moscow State University for some time as professor, and then again in the 90s he moved to the United States, to Los Angeles, to Jet Propulsion Lab. So his main interest is gravity, precision tests of gravity. He's famous for explaining the Feiner anomaly, which was a hot topic in high-energy physics and in cosmology for some time. And today, well, actually, as you know, Nobel Prize was awarded quite recently for exoplanets. And I was listening to the interview of James Peebles about his Nobel Prize, and so he was asked by a journalist what he thinks about exoplanets. He said, well, this is of course a great thing. Unfortunately, we are not going to see, and so Slava is going to argue otherwise.
Excellent. Misha, thank you very much for a wonderful introduction. And thank you all for coming here. It's amazing to see that many people who are interested in the topic that I will be talking about today. So it's nice to be here in Lausanne. It's my second actually visit to this wonderful city. I would like to be here. So it's a very lovely place where lots of history was made, and essentially being here in this audience, seeing that many young people, it's amazing. It's amazing. It's nice because the topic that we'll be discussing today, it's life. So life and how we can detect life, not only on this planet, but elsewhere. And essentially, there are some techniques that we develop here at the Jet Propulsion Laboratory that will help us to actually reach out to those distant worlds and actually to enable us to see those planets. And so being here in Lausanne, it's essentially very, very important. You see life everywhere, and it's amazing, it's nice, very comfortable, very elegant, and it's nice. But how many of you think that there is life exists outside Earth's atmosphere? Can you raise your hand? Yeah, great, I love that. That's amazing, because this is, indeed, this is right. And so you see those people on the space station. This is our friends enjoying their time being on the space station, and they just lovely looking down on our planet, and they enjoy seeing how we live here. And essentially, they're first human beings who are orbiting the planet outside the Earth's atmosphere. And so here, we're interested to see what is actually out there. So here you see that this is the history of space travel, right? You see we started flying in space using Sputnik in 1957. Then today we get into space using Soyuz vehicle, and of course here the Enterprise, right? So Enterprise spacecraft, many of you are aware of, why it is important. So a friend of mine, Alexander Mizurkin, was on the space station. He took this picture last year, 2 years ago, on the anniversary of Sputnik being launched. So essentially, this is a brief history of our space travel so far. So, but moving forward, today I will be discussing quite different expedition that we are developing at NASA Jet Propulsion Laboratory. And this is something that will be will involve using solar gravitational lens. The sun is a lens. So we're talking about applied general relativity here. It's not theoretical discipline anymore. We will use general relativity to essentially use this amplification factor and bending of light, light trajectories, and benefiting from that, essentially look in the very distant places in the universe. And looking at those planets that actually may have conditions similar to our own. They are looking at planets similar to Earth. And then essentially we'll be able to maybe look and make some high-resolution images, or maybe spectroscopy of those worlds. So this is what I will be talking about. And that brings essentially back probably minutes or some moments everybody shared in their childhood. And so look at those.
You ever wonder what's out there?
Oops, the video doesn't show for some reason. So,
maybe someone out there is wondering what it's like here. Cats. Do you think we'll ever meet them? I hope so. Don't you?
So this is what we thought as kids, right? So when you go on the starry night and you see how the stars and what we can think about life in the universe. And essentially, going forward, this is our beautiful family portrait of our planets in the solar system. So this is nice, and at some point, humanity will actually step out of the cradle that we live. The cradle of humanity, the Earth, will leave the Earth at some point, maybe not now, maybe in a few hundred years, we'll start traveling further than the solar system. Hopefully, at the end of this year, some companies will start flying people in space, and we will share experience that is being available only to professional astronauts and cosmonauts. We'll be flying into low Earth orbit, and so potentially that will come in the next couple of years. So, but going forward, looking for life in the universe and the solar system, for example, that's a big challenge. Looking at what we have done in the last several dozens of years, starting from the beginning of space exploration. This is the history of space exploration as we know it. So you see all the planets in the solar system, and pretty much every expedition that we have launched exploring every planet, starting from Mercury all the way to Venus, Earth, Mars. We've been to Mars too many times, and because we are looking for life on Mars, and that was very exciting because at some point we will find some evidence of at least past life and maybe even present life with the reports that we have water on Mars or some water under surface. Potentially there may be life exist even now. And this is, every spacecraft that we launched, we've been there, we've done that. And so we are looking for now the 4 places in the solar system where we hope to find life. Of course, this is Mars. And there are some 2 satellites of Jupiter. And Europa is my favorite because Europa has the ice, the ocean, very thick ice and very deep ocean there. Potentially, when we land spacecraft, we can drill with heat, getting down to the ocean, essentially explore maybe some living organisms on Europa, underneath of ice, thick shell of ice right there. So Ganymede and Enceladus. So these are the places in our solar system where we hope to find life in the next maybe couple, maybe a dozen of years. So we should be able to find something in the local environment. But there are no those green people that we hope to find on Mars, right? So we don't see the evidence that, first of all, we don't see the evidence yet that our planet was ever visited by anybody. And so we don't have the evidence that somebody is living on other planets in the solar system. So by necessity, we have to look elsewhere. And elsewhere would be those exoplanets. Exoplanets is a very exciting field that is emerging now as a very significant field in astronomy, because since the discovery of first exoplanet orbiting the Earth-type star in 1995 by 2 wonderful scientists from Switzerland who was just recently awarded Nobel Prize, essentially since that time we have confirmation by today, roughly 12,000 planets were discovered. And we know that by today, roughly 4,000 confirmed. So there are about 4,500 planetary candidates. And so we know that only 161 of those planets are terrestrial. That means that they're rocky planets that may harbor conditions similar to our Earth, but we don't have confirmation for that yet. So what I'm saying is that given the fact that in our galaxy alone, we would expect to see trillions of planets, trillions, it's a lot of planets. Every year we have at least maybe 1 to 5 stars are being born in the galaxy. And so there may be many planets orbiting those systems. And so essentially we know that there are plenty of systems that we discover that multiple planets are orbiting the star. So our solar system is not alone in the sense that we have 9 planets. And so essentially going out there, there are systems that have already 10 planets. So planets are common in the universe. So it's only a matter of time when we will find the planet which will resemble conditions similar to our Earth. So we need to find a planet that will have a very low eccentricity in its orbit. We need to find a planet around or the star that resembles our own star. And so it should be in a habitable zone. We call habitable zone is the zone where water can exist in 3 conditions. So it's in 3 states, essentially. So once we find these planets which are in this wonderful habitable zone, we can expect we will be able to find signs of organic life there. And so how we do that? We will probably do a lot of spectroscopic studies. We will be able to find methane, oxygen, nitrogen in the atmospheres, and then we have a very good confirmation that indeed there are some planets that harbor life. And then in the next maybe a few tens of years, we should be able to have many of those discoveries made. Now we have, what, as I said, about 10,000 planets discovered. I would say maybe in a few years there will be 20,000, and maybe in a few later on we will have plenty of systems discovered. So this is an amazing field which is extremely fast evolving. But for now we are able to find only big giants, Jupiters, Neptunes, around other stars, because our techniques are not that sensitive to find tiny ones that resemble the Earth. And so I will show some slides why we cannot do that at the moment. But in a few years, as I mentioned, there will be many of those systems. And so what will we do next? So what is the next step? Looking at this map, you see that these are the stars within 100 light years from us. So essentially, and those systems that already have planets confirmed that orbiting around those stars. So you see that even on this map, within 100 light years away from us, there are plenty of planets already discovered. And so it's only a matter of time when we will find the planet that essentially will resemble our own Earth. So we rapidly develop different techniques. Radio velocity is one of them. We should be able to go from roughly now 70 centimeters a second. We'll probably will reach 10 centimeters a second, maybe even lower than that. Then we face a lot of systematics. And so we'll be using transits. Transits when the planet is going around going through between the observer and the star, and essentially transiting the disk of the star. When you see the luminosity of that star is dropping periodically, then you are able to confirm that there is a planet orbiting that system. So using these 2 methods, we can find a lot of different planets. And so you know that NASA and European Space Agency develop a lot of missions to do just that. And essentially, this is some of the missions: Hubble, Spitzer, Kepler, TESS is now in space, bringing a lot of interesting discoveries using transit method. And so there are lots of systems that lots of spacecraft that are being developed, but none of them actually see the planet directly. We have only evidence of that the planet is present around the system, because we cannot uniquely see this planet. We only see the evidence that, yes, something is pushing that star, and because that star is being periodically pulled by gravitational field exerted by the planet. Essentially, it's thinking about it as a binary. You see the optical center of the star moves a little bit, and so you can hypothesize that around that planet, around that star, there is a planet. So, but we cannot see those planets directly. So it's a challenge, and the challenge is really this: the size. See, this is comparable. This is the sun, and this is what we are looking for. So Jupiters, it's easy to find. They're bigger, they're heavier. So, and essentially, they move the sun essentially by significant amount. And for an observer outside the solar system, they would see the sun also moves in its barycentric frame, essentially because it's being pulled around by those giants. But we are not looking for those ones, because they do not have life as we know it. We're looking for those little guys, the small ones, the rocky planets. So this is a challenge that we are facing, the size. And then in addition to that, the distance. So this is a wonderful selfie of us, of you and me sitting in this room, taken by Cassini spacecraft. Cassini took the trip around Saturn, as you know, and then essentially it looked back on Earth. So this is us. This is you and me sitting on this planet, orbiting the sun. But that's the problem that we face. Essentially here, so we are faced with the problem that essentially the size is really an important thing. For example, how big should be the telescope if you want to measure or observe an exo-Earth, the planet similar to our own planet, at 100 light years away? How big should be the telescope? Just simple diffraction optics, as you know, lambda divided by wavelength, divided by the diameter of the telescope. That should give you the sort of result how big should be the telescope. It is 90 kilometers. 90 kilometers. Your diffraction limit gives you the fact that it's Los Angeles. By the way, those of you who are familiar with Los Angeles, Jet Propulsion Laboratory here, Dana Point is there, on the way down to San Diego. So that's 90 kilometers. It's only 10 kilometers shy from the von Karman limit, which is the distance to space, right? So it's 90 kilometers, the diameter of the telescope you must have before even contemplating ability for direct observation of exo-Earth. Our Earth, it's about 13,000 kilometers in the diameter. If you place that object at 100 light years, that's what you need to have. And so, but we, with wonderful technologies that we have with the cell phones that we use, we're all accustomed to multi-pixel resolution images. We want this. We will not be happy with just one pixel. We all want this, right? This is what we're interested in. So, but then if you want this, that's even challenging. So that's Earth, that's the moon, right? So simply multiply the diameter of 90 kilometers by the number of pixels you want to get. If you want to get 1,000 by 1,000 pixels, you're talking about 90,000 kilometers suddenly. It's a significant fraction. So, but that's the challenge. And the challenge is that the current telescope technology is not progressing that fast. So that's what we can do today. Starting from, let's say, I will just show this is the largest telescope that is being built. It's a European extremely large telescope, which will be 39 meters when it will be complete by what is 23, by 2023. This is 39 meters, and that's the size of the telescope. You see the human, the car is here, just for comparison. So that's what we can do. And so those technologies, for example, also here you see this is Arecibo, just for comparison, right? And that was the plan for radio telescope, an overwhelmingly large telescope that was not built essentially. This is what we can do today, on the ground. And it's much easier on the ground, right? And yet, it's still, we are limited by 39 meters, not kilometers. So now we're talking about space. In space, when you fly something in space, we want to fly, soon the next year we'll launch Webb telescope. James Webb telescope will be 6.5 meters in space. It's a challenging technology. You cannot fly it at once. You have to have a segmented mirror. And when you fly this in a launch vehicle, essentially you unfold the petals of the telescope, you fold them, and you put them together so that they will work with the surface that will be controlled comparable to the wavelength that you observe, roughly 1 micron. So if you want to use optical technologies, whatever you build in space, or whatever you build on the ground or in space, you have to control wavefront to the wavelength that you are working. So essentially, if it's 1 micron, the surface has to be accurate to 1 micron. And coming back to this 90 kilometers idea, right? Suppose sometime in the future we'll develop the technology so that we'll be able to build few atoms thick mirror in space, and you will be able to actually launch it in space, however you will do this. You will unfold this 90 kilometers. Solar radiation pressure will remove this object from the solar system in 1 year. Because essentially it's a big sale, right? So you put it up there, you spend a lot of money, you actually assemble it, but no, it will not be stable, it will not be, you will not be able to keep it in space. So that's the challenge. So this is why we came to realization that maybe we need to look for drastic measures. And those drastic measures, essentially those that offered by the solar gravitational lens. Because solar gravitational lens, it is something that was discussed earlier by Einstein himself. When he was actually putting the numbers together, he understood that bending of light is an interesting idea, but it would be very hard to observe. And I will talk about this in a few charts down there. But essentially, we're talking about the ability, natural ability of the sun, the solar gravity, essentially, change the trajectories of light rays. When light travels around massive body, massive gravitating body, doesn't travel on a straight line. Essentially, its trajectories, the trajectories of light are bent towards the body. And the gravitational massive body acts as a lens. And so that lens, in the case of the solar gravity, it's actually at the distance of roughly 547 astronomical units away from us. 1 astronomical unit is the distance between the Earth and the Sun. Voyager spacecraft, at the moment, it was launched in 1974. By now, it reached the distance of roughly 150 astronomical units. It moved was for the 40 years, right? But it was not designed to do that. It just reached those distances by accident, essentially. So we built it expecting it will be working only for 3 years. But 40 years after the launch, it still transmits data at kilobits per second, but still we get a very unique data from Voyager. But now we have developed technologies that will allow us not only to move faster, but also to provide significant data rates from those distances. This is why the idea of solar gravitational lens and mission to that region is very important. So here you see the map of our neighborhood in logarithmic scales. So this is the sun, this is the distance to our stellar neighbor, Alpha Centauri, which is 4.3 light years away. And it is nice to show in logarithmic scale, because otherwise it's a lot of empty space between us and them. It's a lot of empty space. And so this is the solar system, and this is sort of the age of the solar system called heliopause. And so Voyager spacecraft is Voyager 2, Voyager 1, and so essentially the solar gravitational lens is conveniently placed, the region is right in the middle of the picture. So as we fly away from the solar system at some point, so we will be all crossing this distance, because this is where the light rays, which are being emitted by an by an object, for example, Earth-like source, so exoplanet. When you have a plane wave that hits the sun, essentially its wavefront is bent. And so bending essentially forms an interferometric region at the distance that begins of roughly 547 astronomical units out. And so here, in the strong interference region, so essentially you have very high light amplification, because this is where you're essentially dealing with diffractive optics. It's a diffractional gravitational field. And so it's a pencil sharp area where you actually gain a lot, because light amplification factor there is roughly 10 to the 11th. So 11 orders of magnitude. And I will talk about this, because this is something very interesting. In this case, you can benefit from this. And the resolution that you can get, angular resolution, talking about nano arc seconds. And so this is something just came from just the nature of this phenomenon. So now if you put a spacecraft somewhere in this area, and you clearly need to look back at the sun, because if your object is right there behind the sun, you need to be able to block the sun, because sun is not dark. So sun actually shines. So you must have a coronagraph, an instrument that actually blocks the sun. But once you're able to block the sun, and this is our simulations, you see this, once you actually block the sun, you are starting to see the Einstein ring of essentially the light amplified by solar gravity. It all will be in a very thin disk called Einstein ring. And so all the information about exoplanet will be within that Einstein ring. And you need to be able to detect a brightness of that ring and essentially use it to build the image. And so that's actually the idea behind it. And I will talk about this a little bit more. So this is what we want to see. It's a similar Einstein ring that was produced by a nice Hubble telescope. And essentially this is the ring that you have. And if you put a coronagraph and suddenly you block the sun, and essentially this is what you will see behind the sun with this Einstein ring. So, but with the coronagraph, you block it, you block the sun, and you don't need a very significant coronagraphic technique similar to those that are being developed for missions, for example, WFIRST, where you need coronagraph working with 10 to the minus 10 ability to compensate, to block the light to that level. Here we need 10 to the minus 6, that will be more than sufficient. It's not very difficult to do that. And we have the technology that is enabling us to do this right now. So this is what we have, and ultimately what you will get out of that is this. So we all benefit from this magnification factor that is proportional to the ratio of the Schwarzschild radius, which is 3 kilometers, to the wavelength that you use to observe. So we're talking about roughly 10 to the 11th amplification factor, and resolution comes from the sort of the features of the Bessel functions that drives that process. And essentially, the resolution is given by the same lambda wavelength divided by the diameter of your aperture. In this case, diameter of your aperture is the solar diameter. So lambda divided by diameter of the sun, that's where you get this resolution. And so essentially, just a little summary of what solar gravitational lens gives you. It's amplification factor of roughly 10 to the 11th on the optical axis for point sources. And then we're talking about a very high angular resolution of 0.5 nanoseconds. And essentially, if you take an object such as Earth right here, which is as we discussed, it's 13,000 kilometers roughly, it will be all compressed to by the ratio of the distance to the it's the ratio of the distance, heliocentric distance of your spacecraft to the distance to the source. Roughly, it will be all about 1.3 kilometers. So once you, it will be, the image of the exoplanet will be compressed to a cylinder with a diameter of 1.3 kilometers. So if you put a spacecraft within this cylinder, you don't have to stop, because essentially the solar gravitational lens does not form a lens in a normal sense, because there is no focal point, there is focal line. Focal line because it's, the bending of light depends on something called impact parameter. The larger the impact parameter, the further the focusing will be. So as you coast along the optical axis, along the focal line, you can still take the data and use the data for your imaging. So in this case, you don't have to stop. You have to get the speed out to reach this distance in the shortest amount of time. Once you reach the distance, you just continue coasting along and taking valuable data. So that first idea came essentially from Professor von Eshelman. He used to be the chief of radio science team on the Voyager spacecraft, and this is his paper published in Science in '79. And he thought that it would be wonderful to use solar gravitational lens to communicate with other civilizations outside somewhere in the universe. And essentially, he suggested that it would be nice to use it for radio waves. Later on, we showed that for radio waves, solar plasma will be a very significant obstacle. You cannot use the solar gravity lens for microwave radiation, because for microwave sort of range, because solar plasma blocks this type of range. You need to go to very short wavelength for you to go through solar plasma, which is quite important. And so that's the original papers written by Einstein. And you see, if you ever visit Pasadena, so try to go to Huntington Library, where we have archive where this paper is essentially, you can see the derivations done by Einstein, original derivation showing the beginning of the understanding of microlensing phenomena. It is right there. And also there you can see a nice letter written by Einstein to an astronomer at Caltech. And you see the date for this letter is 1913. And if you noticed, he didn't have general relativity at that time. It was light bending phenomena was described using the Newtonian gravity and the early versions of equivalence principle. And you see that bending of light is twice less than we know it today. So based on just Newtonian gravity, you can estimate 0.84 arc seconds. Today we know that it's definitely 1.75. It is interesting to see that was the beginning. And so, but then he wrote the letter to Hale saying what would it take for astronomers to observe bending of light during the solar eclipses. During those sort of interesting phenomena. And Hale reluctantly said, it's not really interesting. Maybe it's difficult, let's not talk about this. But there was a German expedition that actually was motivated to do the experiment in 1916. In 1914, it was the first attempt, but unfortunately the First World War started. And essentially, that expedition was, the eclipse was going through in Crimea in August 1914. And that expedition got captured, essentially. And so they were released later on after the First World War was over. So they continued practicing astronomy, but that was the first attempt, unsuccessful. Later on, we know that Eddington was able to confirm the existence of this effect. And this is the letter written it's a telegram written sent by Campbell to Einstein, saying that 3 pairs of Australia-Tahiti eclipse plates measured by Campbell essentially the light deflection calculated gave Einstein deflection between 1.59 and 1.86 seconds. So confirming the general relativity is correctly describing this very important experiment. And so you see those Eddington and Einstein sitting in Cambridge. It was a very unique time when gravitational experiments, essentially by conducting experiment, before you conduct experiment, you will have 3 possible outcomes. that first of all, the light travel will not be affected by gravity, so deflection would be 0. Then, as I mentioned, Newtonian arguments based on Newtonian gravitation would give you twice less the amount of deflection, the light deflection. And then, of course, the Einstein's general relativity gave 1.75. So 3 possible outcomes. Today, we usually, in fundamental physics experiments, we usually measure 0 because we don't have very clear predictions. So measuring 0 is a frustrating moment, but back then it was very exciting. You have 3 possible outcomes. And of course, we know that indeed, general relativity works well, not only there, but everywhere pretty much. Today, we see those arcs, the microlensing events, they're everywhere in the universe. And you see those confirmations that general relativity works not only in the solar system, but everywhere. And so this is a wonderful sort of testament that indeed general relativity works well. This is my laboratory. This is solar system is my laboratory. I have many spacecraft that are orbiting different planets, and I was part of development of many missions elsewhere. And so how well do we know gravity today? We know gravity quite well. So essentially, this is the little history of the tests of gravity in the solar system. You see possible 2 parameters that would describe deviations from general relativity. Parameter beta would describe nonlinearity of gravitational superposition. Parameter gamma describes the curvature of space produced by unit mass. And of course, general relativity predicts that both parameters, gamma and beta, equal 1. As we've flown multiple missions and we have done multiple radar experiments, you see we've done ranging to Mercury, Venus, Mars, ranging to spacecraft, Mariners, Vikings, Pioneers. We've done a lot of VLBI measurements, global positioning system, a lot of different measurements. Now what we have? So we started with Viking lander on Mars, which constrained parameter gamma to 10 to the minus 3. Then we started, ranging to Mercury, constrained both parameters a little bit. Then further, you see VLBI, astrometric very long baseline interferometry, constrained parameter gamma to less than 10 to the minus 4. Then, of course, lunar laser ranging, another wonderful experiment, constrained this parameter space even further. Then Cassini spacecraft came along and said essentially, any theory of gravity that you can come up with, constrained by solar system test, has to live somewhere inside this little box. So any possible deviations from general relativity that we can come up to explain modern phenomena, modern problems, has to be somewhere inside. And later on, spacecraft ranging even further constrain this possible deviation. So as we know, the solar system tests of general theory of relativity, confirming general relativity to very high precision. And we know that essentially Nobel Prize was awarded for confirmation yet another prediction of general relativity, gravitational waves. And so today, in my mind, general relativity is already being 100 years old. It's time to think about applied general relativity. And indeed, before we plan any mission, we have to plan general relativistic contribution to even landers on Mars. We're thinking about flying people on Mars, right? And so the idea is to fly first a cargo that would bring a cargo spacecraft that would bring supplies and some energy storage and something for the people then yet to fly further. The second spacecraft will bring humans. If you don't account for general relativity, your error will be about 40 kilometers on the surface of Mars. So you land humans, if you don't have visual confirmation, you land humans and they would have to get to the supplies. Without general relativity, it takes some time. So, but then of course, a wonderful triumph for Swiss astronomy, confirming sort of the discovering amazing exoplanet. The first exoplanet was ever discovered. And so in my mind, this is a wonderful confirmation that indeed we are not alone. There are plenty of the different worlds that exist out there. And so confirming that, in my mind, this essentially, it's also Newtonian gravity was used to look for this planet. So it's also, in a sense, a confirmation of gravitational theories that were used to discover the exoplanet orbiting the Earth-like star in 1995. So, but then let me show a little summary of what we just discussed, a little movie that actually deals with the idea of solar gravitational lensing. And so with this, I guess, if I can find my mouse.
Exoplanets. They're just like regular planets, but found in other planetary systems besides our own. So far, over 3,600 discoveries have been confirmed since 1992. These fuzzy dots are a few examples of the best direct images that we've got, and these are all gas giants like Jupiter. What we don't have is a really good image of an Earth-like exoplanet. It may actually be possible to get an image like this, but how we can do it may surprise you. we could use the sun as a lens. The sun is massive, to say the least, therefore so is its gravitational effect, which warps the very fabric of space itself. When incoming light from a hypothetical exoplanet approaches the sun, its path is also warped. These curved light rays are brought into focus starting from about 550 astronomical units away from the sun. The effect of gravity on the deflection of light is inversely proportional to its distance from the center of the sun. Approaching light rays further from the sun are not curved as much as light rays closer to it, so they come into focus past 550 AU, which results in a focus line rather than a single focus point. This is the Solar Gravitational Lens. If we take a 1-meter telescope, place it at 650 AU away on the focus line, targeting an exoplanet 100 light years away, how much magnification and resolving power do you think it will have? From a fuzzy dot to a slightly larger fuzzy dot? Not even close. It could resolve details at the scale of 10 kilometers squared. That's like resolving the width of a single human hair on the moon from Earth, or an equivalent resolution like this image of Earth. If instead you targeted the closest exoplanet to us, Proxima b, at about 4¼ light years away, the resolution would be even greater, in the hundreds of meter scale. But there are not as many planetary systems to choose from right next door to us, relatively speaking. The sun, obviously, does not function exactly like a conventional lens. The sun's gravitational force warps the incoming light in addition to focusing it, resulting in a ring shape around the sun called an Einstein. Correcting this is a lot more work than a deep warping filter in Photoshop. Adding to the difficulty, we can't resolve the whole Einstein ring at once with just a 1-meter telescope either. If this same example exoplanet has an Earth-like diameter of around 12,700 kilometers, then that will result in an Einstein ring approximately 1.3 kilometers thick. This animation isn't to scale, as a ring would look more like this compared to the sun. But with those variables in mind, the area of the focus line that our telescope needs to cover would be a cylinder with a diameter of about 1.3 kilometers. You would need a telescope that's at least that size to resolve the entirety of the Einstein ring in one picture. That's 206 times larger than the primary mirror in the Hubble telescope. Fortunately, you don't need to resolve the whole ring in just one picture. Our 1-meter telescope can image an area on this example exoplanet 10 kilometers squared. So you can think of each picture it takes as a single pixel. You can still resolve the whole ring, you just need to assemble it pixel by pixel. The proposed goal is for a final image with 1000 by 1000 pixels, but that'll take some time as that adds up to a total of 1 million pictures. Before the imaging process can even begin, something has to be done about the sun. The telescope needs to face the sun to image the exoplanet, but unsurprisingly, its light would outshine the exoplanet. Since the Einstein ring is around and outside the sun, an internal coronagraph can be used which blocks the sun and the brightest part of the corona. There will still be some light from the corona mixed in, but not enough to completely overwhelm the exoplanet's light. For the coronagraph to be more effective, the telescope needs to be positioned further back on the focus line. That's why we can't place the telescope right at 550 AU, but still not too far back, as that could add years to the mission timeline. A good compromise would be between 650 to 800 AU. When the telescope is further from the sun, naturally it will appear smaller. The magnification of the exoplanet stays the same, but the Einstein ring is now at a greater distance from the sun's surface, so there's less corona light to contend with. But how far away are these distances really? An astronomical unit, or AU, is the distance from the Earth to the sun. At its greatest distance from the sun, Pluto is almost 50 AU away. Voyager 1 is currently traveling through interstellar space at 138 AU away from the sun, farther than any spacecraft has traveled. The telescope needs to be almost 5 times further than that. That distance, while considerable, may not be insurmountable. Here's just one possible hypothetical scenario. Using the currently in development SLS rocket as the launch vehicle, the spacecraft can get to Jupiter within 6 months. It can use a gravity assist at Jupiter, slingshotting the spacecraft towards the sun. As it falls into the sun's gravity well within 5 to 7 solar radii, its velocity dramatically increases. When the spacecraft reaches maximum velocity through this maneuver, its rocket engines fire, adding to its acceleration and sending it on a trajectory to the focus line. Traveling between 17 to 22 AU per year, the spacecraft can get to 650 AU in about 30 years in the most optimistic scenario. But no spacecraft has approached this close to the sun before, so a fairly robust solar heat shield will have to be designed and employed in order for the spacecraft to survive. Once there, the telescope has to move with the focus line and within it, as nothing in the universe is static. The exoplanet orbits its parent star while also rotating around its axis, if not tidally locked to its own star. While the trajectory design can account for much of this, a novel design for the spacecraft itself is still needed for it to move stably within the focus line. One idea is to build a spacecraft with the telescope on one end, tethered to a counterweight at the other end, using ion thrusters for propulsion at this point. The telescope can be pulled in or extended out along this tether to move within the focus line while maintaining a stabilized anchor position. This enables the telescope to gather a sufficient amount of images with less difficulty than keeping an untethered spacecraft stabilized. Using this method, it should take around 3 months to finish the task. But the challenges don't end there. Each image that the telescope takes is not a neat slice of the full ring. Instead, the telescope builds a rasterized image where each snapshot contributes more detail and magnification of a specific area on the exoplanet. These images end up overlapping each other, which can be considered a benefit as we won't need quite as many pictures for the desired resolution. Next, a deconvolution algorithm will be needed to fix the warped ring. While that may be a considerable challenge, we'll have the variables we need to correct it. The position of the spacecraft, brightness of each image at those positions, and the optical properties of the solar gravitational lens. If we are able to overcome all of these technical hurdles, we will finally have our first high-resolution image of an exoplanet. Using spectroscopy, we can analyze the light from the exoplanet in more detail than ever before. Gases absorb and emit their own distinct wavelengths of light. So when we analyze light from its atmosphere, we'll be able to accurately define its composition. Is the air breathable? Are there any telltale signs of life in the atmosphere, like methane, for example? Suppose there's actually intelligent life, and they too have electricity. Well, if it's nighttime and they turn on the lights, we'll see them. But there's more. Radio waves are just another wavelength of light. If ET is broadcasting, those radio transmissions will also be magnified, but not to the extent of visible light, as the radio spectrum is actually distorted by the interference of the sun's corona. While utilizing the solar gravitational lens is a daunting technical challenge, it still may be achievable in the near future. In fact, NASA's Innovative Advanced Concepts Program, or NIAC, recently accepted a proposal led by Dr. Slava Turychev.
That's about me. I will not be talking about, I will not let you to listen to this, but it's available on YouTube. So essentially, that's the general idea behind this approach. Now let's put numbers together, because essentially the idea is idea by itself, but then what are the fluxes do we expect? What is the signal-to-noise ratio? Because when you plan for experiment, when you design a mission, you have to know what you're trying to observe. And this is what I will be discussing in the remaining time. Essentially, the signals and the fluxes. Essentially, what can we do? So this is the idea. If you have the source somewhere at the distance far away from the sun, essentially you send a spacecraft where the image is produced on the image plane. As I mentioned, it's beyond 550 astronomical units. The image on the image plane. So if you put a telescope, if you put an optical telescope that will be able to imaging telescope. So then imaging telescope will see the Einstein ring right there on its focal plane. So if you're dealing with the point source and if you're perfectly aligned with the optical axis, you will see the Einstein ring on the left. If you slightly deviate from the optical axis, you will see how the Einstein ring breaks into the arcs, and that's what you would see. If you deviate further, the information from that point source will be contained in the two blobs. We are still within the strong interferometric region, so we are not getting into the microlensing regime where you don't see one of the objects, you see only one. So we will still see the two blobs. And that's something that we need to take into account when you start estimating the signal fluxes from those sources. Initially, we did the photometric detection. Photometric detection, it's when you see the sort of the resolved object. We're not talking about point sources anymore. It's an extended resolved object. And the image plane, you see those the fuzzy image, because solar gravity lens is not a good lens by itself. It has a significant spherical aberration, and that aberration results into the blurring the image. See, the image blurring is quite evident, and I will talk how we're able to deal with that. Essentially, we need to be able to talk about three-dimensional structure of the problem. It's not one dimension; it's three-dimensional. So we have full formalism to describe three-dimensional optical properties of the slow gravitational lens. So we are able to take into account to estimate the fluxes. For that, let's just walk you through very briefly what do we do. Initially, we have the resolved object somewhere at the distance, let's say 30 parsec away from us, which is 100 light years. So on the image plane, you have a significant the object image. If this is the Earth, which is 13,000 kilometers, this is only 1.3 kilometers. And remember, we are not flying telescope with 1.3 kilometers because it's very, very expensive to do that. So we fly a meter-class telescope. Meter-class telescope is only part of that image. So we observe, placing a telescope of meter telescope only within the image, there is a directly observed region on the exoplanet, and the rest of the planet provides blurring contribution. So what do we do? The full signal essentially is computed using the approach that we developed, taking into account the sizes of exoplanets, the distances, the geometry, and we're able to compute now all the fluxes. The blur, if you position it exactly at the center of the image, the largest blur will come exactly here. But if your telescope is a little bit further away, if you position your telescope at the end of this image, it will be less blurring coming into the picture. And so essentially, it's interesting. It's comparing the two, the directly imaged region provides that signal, and the blurring is given much stronger. The blurring essentially amplifies the signal by about 1,000 times. So essentially, it's a kind of shadow imaging. What I mean by shadow imaging is that when I point a telescope somewhere on the image, and I don't really see the information coming from the directly imaged region, I see significant brightness from the other part of the exoplanet. As I move, the brightness changes. As I move further, brightness changes. So I recover the real image of the exoplanet by actually doing deconvolution, actually getting into that information. So we're able to do that. So with this technique, we're able to actually start estimating the signals. So if we assume that the sun is dark, there is no corona, essentially, for the planets that we deal in, what we plan to work with, let's say 1.3 parsec, which is closest planet to us, and then 10 parsec, which is it's about 30 light years away, and 30 parsec, about 100 light years away. We're talking about flux of roughly 10 to the 5 photons a second using solar gravitational lensing. So this is very significant, even for most distant planets. If the planets are kind of in a reasonable distance, 10 to 20 parsec away from us, we're talking about 10 to the roughly 5 times 10 to the 5 photons a second, which is a quite significant flux. Now, detection sensitivity in this case is, we're talking about signal-to-noise ratio of roughly 500 in 1 second. So with such a significant signal-to-noise ratio, we can deconvolve the image with no problem at all because we have a very strong signal. Remember, we are not taking into account solar corona yet. So here, if sun is dark, it's very easy to actually get the data and recover the image. So this is what we deal with. So this is the image of our Earth in black and white. And then this is what we will be observing, because solar gravitational lensing, as I mentioned, it has a significant spherical aberration. This is the blurry image that we will have to sample pixel by pixel. But then with the significant signal-to-noise ratio that we have, we're able to recover the images right there. So with taking enough data, let's say within a year, we should be able to reach pretty much the same image reconstruction. So this is within a few weeks. You don't see much. You see sort of blur, significant blurring of the image. And then as you move on, you're essentially able to reconstruct a very interesting features of exoplanet. Initially, we thought that it will be wavelength dependent, but really when we deal with extended sources and with the finite size of the telescope, the dependence on the wavelength is secondary, it's a second order effect. It's not really important. So now we can deal with actually color. So with the color images, this is the Earth, and again with the blur you will see something like this. And now with deconvolution algorithms that we develop specifically for that, we're able to recover. And so there is still some artifacts, but I think they're not really significant. We just need to improve on them. So they still see the blur is taken away, and pretty much you can recover the main features of this object quite well. As I mentioned, this is still, the sun is dark. But now let's deal with this. Solar corona is the most significant source of noise, and the sun is bright. When the light travels through the solar corona, it's not really affected. Its phase is not really affected by contribution from the solar corona. Radio waves are affected significantly, but for light, it travels through solar corona with pretty much no effect at all. I mean, very, very tiny. But the brightness of the solar corona provides a significant source of noise when you do when you do detection. And the effect of the sun, for example, when you have the solar gravity, when there is just plane wave hits the sun, it's just a shadow. If there is no plasma and there is no gravity, it's just this sort of spherical obscuration. It's this shadow, just a straight cylinder, pretty much. We're not talking about Arago spot in the middle here. It's so for now, just that way. But if you have plasma only, plasma essentially has negative refraction index. So plasma actually pushes the light out. Solar plasma. It's not like Earth atmosphere that focuses light. The plasma in the sun pushes light out, defocuses. That's what plasma does. That's why when we deal with microwave frequencies, that effect actually destroys the focusing of gravity. It contemplates gravity. Because here, pure gravity only, gravity focuses light. And both of them, gravity and plasma, they contemplate each other. And so when we deal with microwave, essentially the refraction in plasma is stronger than gravity in this case. So, but with optical, it's not a problem. So, effect of solar corona on light amplification, we just showed that indeed it's not a significant problem. So, light amplification of the solar gravity lens is not affected significantly by the solar corona. So, essentially, we're able to reconstruct all the properties with no problem. But let's talk about the noise. So this is the properties of the solar corona. Einstein ring, when we at the distance of 600 AU, we are very close to the sun. We don't want to be exactly at the edge of the sun, because when we started 547 astronomical units, Einstein ring is touching the surface of the sun. We don't want that because it's a very turbulent regime. It's very hard to be there. We want to travel further so that impact parameters will be larger, therefore will be further away from the sun. Starting with 600 AU, we're already right there. About 1500 AU, so this is the area where we need to be, essentially. And so this is how we model the detector. So when we start with the multipixel detector in the focal plane in our telescope, you see the Einstein ring. So it's right there. For any given distance from the sun, it's pretty much, you know how to calculate it, so it's very easy. But we assume that the sun is dark here. Now we put in the sun and the solar corona, essentially. Not only the sun, which is important, but solar corona. It illuminates every pixel on your detector. Moving on, you block the sun with a coronagraph. And so essentially you don't get much light from the sun. Moving further, with the telescope that you have a diffraction sort of element. Telescope resolution is very small. We don't resolve the thickness of the Einstein ring, but we're able to see the entire thing. So now this is the disk where we get the light from when we deal with the solar gravitational lensing. And so this is how we compute signals. So moving further, so we can actually tell the detector, don't give us the information from the pixel that we don't want. And essentially, we can collect only the information from within this sort of circumference that we're interested in. So that's how we compute the light, sort of the signals. Now a little bit more on the typical angles. So this is the sun at the distance of roughly 800 astronomical units. It subtends an angle of 1.3 arc seconds. As you move further away, essentially this is the typical surface brightness of the solar corona is seen at this distance. So the Einstein ring will be within this sort of region. That's what we need to take into account. And essentially when we observe the light, essentially we're able to compute how much actual photons do we get from solar corona into the telescope. Moving forward, just a little bit more information. So this is this is our solar corona, contributes it's actually gets smaller and smaller. And this is the thickness of the Einstein ring as we travel away from the sun. And so these are the signals that we get, exoplanet signals, still at the level 10 to the 5 photons a second. Solar corona is strong. It's about 500 times stronger than the exoplanet. But basically, it's, we can recover that signal, and signal-to-noise ratio in this case is very impressive. So we can actually compute the signal-to-noise ratio roughly 100 in 1 second. So by actually sizing up the experiment, we were able to recover quite a lot of different pixels from exoplanet, taking into account presence of solar corona. If we allow for 1 year of integration, for different planets, we can talk about 300 pixels resolution for the closest planet, and roughly, I would say about 70 pixels resolution for the most distant planet. So now we're talking about that even with this technique, we're able to get resolutions of roughly 100 by 100 pixels within 1 year. And if you integrate longer, as you reach those distances, you don't stop, you just continue integrating signal. Just for the sake of argument, essentially within 10 years, we're able to make an image, high resolution image of that object with roughly 200 pixels across, 200 by 200 pixels of an exo-Earth, which is situated roughly 100 light years away. And so that's the challenge. And that's the solution. Essentially, with this technique, we will be able to point to an exo-Earth, and we'll be able to collect enough photons given the strongest signals and the noises available in the system. Still, we're talking about not single pixel, we're talking about hundreds of pixels of those images. Maybe not thousands pixels, as we all want, right? But ultimately, if you integrate longer, if your mission survives longer, or if you fly not one spacecraft, but multiple spacecraft. So now technology is allowing us to think about small and very capable spacecraft. We're not talking about single system, we're talking about multiple systems. If you launch, let's say with the Falcon Heavy, you launch several spacecraft and all of them travel in the same distance, potentially you can reach this region and start taking pictures. So essentially, if you have a number of n spacecraft, essentially you can talk about multiplying number of pixels by pretty much just linearly by number of spacecraft. You fly 2 spacecraft, you're talking about 500 pixels resolution of that exoplanet because integration time cuts significantly here. So that's the idea. So now how do we reach those distances? Reaching those distances is not that simple. So the challenge is that our chemical propulsion is very limited. With chemical propulsion, essentially, you see it requires significant propellant at launch. And essentially, we need to still get very close to the sun. And even then, when we fly towards the sun and we start this very strong maneuver at the closest approach to the sun, we still get the velocities of roughly 15 astronomical units per year. We need 20, 25 to reach in a reasonable time to get to this region. The most difficult, the most challenging problem in this mission is essentially reaching this distance in a short amount of time possible. And usually people, there are 2 solutions to that. It's one solution is fly faster, and the second solution is live longer. So and I would argue we need to work on both. So in this case, because ultimately you want to see the results within the lifetime of a scientist, because that's what we like. It's human beings. So clearly here technology is required to fly faster. And so solar thermal propulsion gives you 22 U per year. Nuclear electric, which is being developed now, we're still talking about 20 U per year. Electric sail also provides an interesting capability. We decided to focus now on solar sailing. Solar sailing technique is something that when you fly by the sun very close, you can use the large foil that you unfold in your spacecraft and to capture solar photons. And essentially, solar photons transfer momentum to your system, and you actually can get very high velocities. So here's the idea of flying a spacecraft that was developed, prototype was developed for different program. And so, but with the solar sailing spacecraft, we are able to reach velocities of roughly 20, 25 AU per year, which is what we want. And essentially, once we eject this system, it's very autonomous. It can change the orientation, and the large sail can be used for multiple purposes. For example, the sail that we'll be using for the Solar Gravity Lens spacecraft can be used as antenna, as a collecting area for the telescope, and can be used for multiple other things. So we can repurpose different structures on the spacecraft. We can actually do a lot of other things with this. And if you fly a bunch of those spacecraft, potentially you can distribute functions among different spacecraft. And so the examples of this, it's one of these prototypes was developed by a company Lagarde in Southern California. And another one is a typical star shade that is developed for WFIRST spacecraft. It was developed at JPL, but the structures exist and they can be used for the mission that we discuss. And so the history of solar sail in spacecraft is very abundant now. We have multiple systems flying, and so, but yet we need to demonstrate that we are able to reach high velocities. One of the missions that we are pushing with would be to chase one of the interstellar objects that started to visit our solar system. Already the second one was detected this year. So once these objects, asteroids or comets, would go through the solar system, with this type of approach, we can intercept those objects, we can fly, we can sort of play Don Quixote. Essentially, we can drop something on those and see spectra sort of those objects we can study. But this is the same technique will be used for solar gravity lens, and it's a fast transit through the solar system and actually moving to very high velocities. That's the type of spacecraft we're thinking about. I'm not going to be spending more time on that. If you're interested, we can discuss. And that's pretty much the mission scenario. So we would like to use the rideshare opportunities that now seem to be very available from Falcon spacecraft that being launched every year. Falcon Heavy will be amazing capability. Then Blue Origin develops another mission that will be able to fly us very soon. So anyway, we use rideshare. We assemble somewhere on low Earth orbit, on the rendezvous orbit, then a bunch of spacecraft. We will use the string of pearl approach, where we fly multiple small, inexpensive spacecraft. We'll assemble them in low Earth orbit, and then basically all of them will start flying towards the sun. And in spiraling takes about 3 months in spiraling towards the sun. And once we're flying by the sun, they will unfold their sails and will reach very high velocity pretty rapidly. So near Jupiter, when you're flying by Jupiter, we may still keep the sail, or may just drop part of the sail, or drop the entire sail together. So, but it's still a possibility, because after Jupiter, pretty much solar radiation pressure is negligible. We don't need it. So we just needed the first puff. When we go through the sun, we just use it at this moment. And so as we then approaching the solar gravity lens region, we can use the magnified light from the parent star as a guidance, because not only light from exoplanet is amplified, but it's the light from the parent star is amplified as well, much stronger than the light from the exoplanet. So we can use that light from the parent star to find the focal line, and then from that we can go down to where the exoplanet is. And in fact, because solar gravity lens has such a strong sort of point spread function, the light from parent star does not affect the light from the exoplanet, so it's not a problem. And so with this, I'd like to conclude. That's pretty much a conclusion of my short, long presentation. So we have a very good understanding of solar gravitational lensing. It seems to be offering very unique capabilities that are not available with any other technique. Period. Nothing similar to that is available. Using optical techniques such as telescope and interferometers, you see that it requires a significant megastructures in space to do anything like that. And so the progress that we have in multiple programs in ESA and NASA, so focusing on building ever larger telescopes. And ever larger, now we have 6.5 meters will be launched. And so we can expect that will be 15 meters in space at some point. But 15 meters in space will not allow us to see anything close to what we want. So ultimately, that is something that we need to keep in mind, and that's why NASA is investing some funding to start moving with this mission. We are moving within JPL. We are developing a very large collaboration within many organizations in the US, and also European colleagues are joining us. So at some point, we hope to be able to develop this mission in flight for the sake of for sort of studying the light from studying the image of exoplanet. If one day we wake up and the major newspaper shows the sort of the big title saying the first habitable exoplanet is discovered, we all know what to do. We need to go opposite direction from that exoplanet to the solar gravity lens focus for that exoplanet, and then taking the data and essentially observing it. Clearly, it's a one target system. It's a one system target. So essentially, what I say, it's the telescope that will observe only one target. So essentially, it's a challenge, but I would say it's not only one planet, it's actually the system of planets orbiting different stars. And so as we go way along this trajectory, we can do multiple other sciences I didn't talk about. But again, it has to be high-value target, so to speak. So if we definitely have a confirmation that there is some clear evidence for life on that planet, that's the solution. So thank you very much. If you have any questions, I would be happy to answer.
Thank you very much, Slava, for this exciting talk. So questions?
So being a one-target system, how are you going to go about choosing one of these? I mean, what level of evidence do you need to say this is the exoplanet I would be excited to send the spacecraft to observe?
This question arises only because of the perception of the high cost of this mission, right? So if the mission is inexpensive, then this question is not that strong, not that complicated. When people decide where to land on Mars, you have to be present on those meetings to see who will win that will land here, but not there, behind that mountain. It's a very challenging question. Here will be the same. So essentially, we need to have a good confirmation that indeed this planet has atmosphere, evidence for atmosphere, and maybe seeing confirmation that there is some evidence for nitrogen, oxygen, methane, that would help. But ultimately, if the cost for this mission will be not as critical, we can fly multiple of them. And so it is likely that we will reach that state because we think about the cost of the spacecraft is very affordable. It's not those billions of dollars that we want to spend on those, but the mission will be still expensive. So as we work on this mission, we think that maybe multiple spacecraft can be launched in different targets as exploratory mission. It still will take some time, and that's the challenge. The time, the biggest challenge is the time. And so, of course, we human beings, we hesitate to make decisions that will pan out later on, right? And so that's a decision we have to sort of deal with as we approach that point. But I appreciate that question. We don't at the moment, we don't have clear answer as to how to choose the target. But it's basically based on the evidence that indeed, among the list of targets that we have, short list of targets, this will be the most exciting one to go.
So you have such a short list?
We have few, for example, TRAPPIST would be nice. It has 10 planets, and we can observe every one of them. So as we go to systems like that, you can observe not one planet, but multiple of them, because ultimately what you see is that one planet, at its furthest from its parent star, it's easier to observe, because when it goes, when it transits its own star, the background will be very strong. It will be very difficult to observe. So at that time, we don't observe. We just observe other planets orbiting the same system. In a sense, we'll get a lot of information about how those planets are formed, a lot of information. We will start doing sort of a comparative studies of exoplanetary systems, which is just the field is yet in the science fiction yet. I mean, we think about this, but there is no technique really that can let us to do that. Here, we're talking about exactly this. And so we can talk about spectropolarimetry data, we can talk about spectroscopy, and spectroscopy, because you have a very high signal-to-noise ratio, essentially in broadband measurements. You can split this, your, let's say, observation wave broadband from 0.5 micron to 1.5 micron, or maybe to 2 microns, and do a sort of very narrow spectra here, and you can detect spectral compositions of different constituents there. And if there is some, organisms living on that planet, we at least know if they use the same the same technology to drive fuel as we do. Do they waste their environment as we do? So at least there's something that we can study in many ways. But posing this question scientifically, you really need to have high evidence that indeed that planet is of very high significance to us. And so ultimately, as we go through exoplanetary discoveries more and more, we will start collecting the list of targets which are resembling our planet. And then when we have maybe a handful of them, why don't go there? And so that's something we need to decide at some point, hopefully soon.
The planet will probably be spinning around an unknown axis. So since you don't see the whole picture at once, this will probably complicate and lengthen the whole story, right?
Absolutely. Very good question. Nothing is static in the universe. And so not only the planet is spinning, it also orbits its own star. That star has a proper motion with respect to the sun. And our sun is not stable either, because the sun is being jerked around by Jupiter and Saturn, and so by those planets. With respect to solar system barycenter, the sun is moving. And so, but this is the largest motion we need to deal with. So if our mission design will be able to compensate for the solar motion with respect to solar system barycenter, no other motions are a problem. So, but this is about motion. But coming back to your question, indeed, the planet rotates. And we will not be able to see full disk of the planet. We'll see only sort of the partial illumination, because it will be, when it at the furthest, we'll see only an arc, sort of part of that, phases of the planet. And so as it rotates, we have techniques, something called rotational deconvolution, which is allowing you actually to get to a super resolution, because temporally variable background allows you to really reconstruct the data peeling behind the clouds on the planet. And so rotational deconvolution allows you to reconstruct very high resolution maps of middle latitudes of the planet. So we have the technique to do that. And it will only be, if we have enough data, and that means either multiple spacecraft or basically a larger aperture. In this case, it's not a problem. So we still are able to get the data about rotating planet, and we hope it is rotating, so within a year of integration.
Yes. Could we use the gravitational lensing of a bigger star, which focal line is points in our direction?
This is what we do. And we do regularly by looking for exoplanets using microlensing techniques. Unfortunately, those events are not predictable. So in the last usually about a month. So before the microlensing gets the highest signal, it's about 14 days when all the observatories started looking at this event. And after it reaches the maximum, it's pretty much after that, in 14 days it's gone, and it's never repeat. So it's hard to put experiments to observe anything and to predict whether or not we can make any sort of intelligent observation of objects there. We can confirm presence of those planets there. But this is the engineering side. We can engineer alignment very precisely here, because this is what we can do. We can build spacecraft, we can design trajectory using the sun. It's a large structure in space that humanity will be able to build. So, but precision engineering on these scales was never been done before. This is what we are actually asking for.
Yes. If there is one day a very high-value target but not aligned with the ecliptic plane, could you remove the telescope?
Yes. Yes. And we have studied those targets as well. It will be challenging to launch, but still with the solar sailing, in fact, we can do that. So because I remember so we can actually, Ulysses spacecraft, European Space Agency and NASA spacecraft, Ulysses was outside, perpendicular to ecliptic. So we can launch spacecraft go into Jupiter and then change orientation, go into perpendicular to ecliptic or any inclination, and then going by sun. Now it's easy. So we can design for any target that we would like to reach. We have the way to actually get to the focal line of that target using solar sail trajectories. Can be done.
Theoretically speaking, could we use a black hole because a black hole has mass and doesn't affect the...
Right, and we had just recently we had very nice confirmation that indeed they exist. The Event Horizon Telescope confirmed the presence of, made the images of black holes. But again, as with microlensing we discussed, there are plenty of black holes available, essentially in the middle, in the center of the galaxies. But the alignment is very difficult. So how do you align yourself with the object you want to observe, and the black hole is here? You need to fly many parsec to get to that focal line. So we are not thinking about this. Effect is there, but it will be maybe not this not within this century. At some point we'll do that, but now we are focusing on something that is much easier, using the sun.
What is your estimate of the date when we can have an image like the ones of your simulation?
We have a large, Thank you for the question. We have a very large group of people now in US. Roughly 7 organizations are exploring this mission. And so we think that most of the technologies are available now. We don't require any new technology, except probably for power sources. And the sailing material, we have the technique how to develop the sails that are needed. Potentially, we are ready to fly in about 12 years from today. So 12 years plus 25 years. So that's the time frame that we can have the image. I would say 40 years from now. So in 40 years from now, we can have an image. Again, the biggest challenge is to get there. If the time to reach the distance will not be that long, we could fly the mission tomorrow. But then basically it is in 40 years we can have the mission like that. But again, putting this in a perspective, Voyager spacecraft was launched in '74, it still transmits, and we still talk to people who actually design it. And so it's quite exciting to see that indeed it is possible. But again, the challenge is the distances where we are. And so when you try to put this together, that's developing faster propulsion. That may be a way to go. But given the technologies we have today, in 40 years.
Regarding this black hole question,
yes.
What if we want to observe black holes instead of observe planets?
That's easy. That's easy in a sense. When black hole is the source, not the lens, we can point the telescope and we can design trajectory to observe the black hole. So again, as we discussed, the challenge would be the foreground and background of material that is being accreted on the black hole. And so, but potentially we can make a much better resolution that even Horizon Telescope did, and we do this in different wavelengths. They did it in microwave, roughly 10 centimeters. We can do this in optical, let's say 1 micron. And so with this, we can study different performance of that object. We can confirm multiple characteristics, whether or not it's a Schwarzschild or curved black hole. And given the signal-noise ratio that I estimated, I think we can do quite well there. So focusing on black hole or on quasars. On quasars, when you have those extreme processes, you can actually do temporal resolution, and we see when the jets are actually forming. You can go into jet forming region. So with this, that's something you can think about, something that is very unique. When we talk about quasars, especially jet forming region, when you actually are quite exciting, you can prove multiple theories how they actually born those objects. And so that's, this technique is now being only studied. We just begin studying it very sort of in a methodical way. So, but there are multiple uses of it. And so if we deal with the sources, obviously there will be multiple of other things. You can do microwave background. You can do a lot of sort of structure. You can expand. You can peek in the very far regions in the universe. So you can get a lot of interesting information about this. I'm sorry. You can do a large scale structure, and you can look at different the early part of universe evolution. So, so with this. With microwave background, you need a different wavelength. So here, potentially doable, but I have not thought I should not claim that.
Okay, last question. Could it be potentially useful to try and do it with a big planet, which has a quite big mass, for example, Jupiter? We would have the problem of the sun's light having to be blocked. Couldn't we do the same with Jupiter, or was its mass not big enough to be useful?
The Jupiter's mass is it's about 1,000 times smaller than the solar mass, and so in this case, the focal region where you need to go, it will be 2,500 astronomical units away. So it's 2,500 AU. It's way too far. Plus, it orbits the sun. You need to chase the Jupiter all the time. It's not stable. So yes, effect is there, but it's not practically useful in a sense.
Okay, so I think, yeah, there is Prof is there. You can still ask
of course.
Slava, and he will be around tomorrow as well. So thank you very much.
Thank you.